Hello students, welcome back to the classroom point. In our previous classes, we have completed the hybridization synopsis as well as the SP, SP2 and SP3 hybridization examples. So in today's class, we shall discuss the hybridization involving the d orbitals. So let's begin the class now. Hybridization involving d orbitals. So in this hybridization involving d orbitals, we know that d orbitals begins from the third period. Hence, second period elements do not participate in the hybridization involving the d orbitals. Only the elements from the third period onwards, they start participating in the hybridization involving in the d orbitals. So now here, if we see the starting d orbitals, here we can consider that third period is having the 3s, 3p, 3d orbitals. After 3d, 4s, 4p is present in the next orbit. So we must keep one point in mind that the energy of the 3d orbital is in between the 3s, 3p as well as the 4s and 4p. Hence, this s orbital, 3s orbital and 3p orbital can intermix with the 3d orbital in providing SP3d hybrid orbitals as well as SP3d2 hybrid orbitals. At the same way, these 3d orbitals can also intermix with the 4s and 4p orbitals because their energy is also close to each other. Hence, these d orbitals when intermixes with 4s and 4p orbitals, it can produce dsp2 hybridization or d2sp3 hybridization. In case of both SP3d and SP3d2 orbitals, the d orbital is present after the p orbitals. That means these are called the outer orbital configurations. So outer side means outside d orbital participated. So these are called the outer orbital hybridizations. And in these cases, d orbital starting only participated. That's why these are called the inner orbital hybridization orbitals. Now, let us see what type of shapes are having these molecules and what d orbitals are participating. In case of SP3d hybridization, the shape of the molecules is trigonal bipyramidal, and here the d orbital participated in the hybridization belongs to the dz square. And in the case of the dsp2 hybridization, the shape is square planar, and the d orbital participated in the dsp2 hybridization is dx square minus y square. And in both of these cases, whether it is sp3d2 or d2sp3, the shape is octahedral, and the d orbitals participated in this intermixing process are both dx square minus y square as well as dz square orbitals. Now let us pick up the two examples regarding this one. So first of all, let us discuss the SP3d hybridization. So in SP3d hybridization, one s orbital, three p orbitals px, py and pz along with one of the d orbital, that is dz square orbital, intermixes with each other and finally produces 5 equivalent energy SP3d hybrid orbitals. See here, 1 d orbital, 3 p orbitals, 1 s orbital, totally 5 are there. So that 5 SP3d hybrid orbitals are present. Example for this SP3d hybridization is PCl5 molecule. So in PCl5 molecule, the phosphorus atom is the central atom whose atomic number is 15. Electronic configuration is neon 3s2, 3p3, 3d0. So it is having a pair of electrons in its 3s orbital, 3 unpaired electrons, and no electrons in the d orbital in its ground state. But to get the 5 bonds, then it must need the 5 unpaired electrons. Hence, one of these s electron directly jumps into the d orbital, providing the 5 unpaired electrons in its first excited state. So now 1 s orbital, 3 p orbitals, 1 d orbital intermixes with each other and provides the SP3d hybrid orbitals. These SP3d hybrid orbitals are oriented in such a manner that, so these are having the 5 orbitals. So in these 5 SP3d hybrid orbitals, these are small negative lobes. These 3 orbitals are in the same plane, so they arrange in the trigonal planar shape, and these 2 are above and below the plane. So that let us try to fill these orbitals with unpaired electrons. So these orbitals are arranged in a single plane, same plane. So trigonal, this is one pyramid, this is one pyramid. It gives the bipyramidal shape. Now PCl5, chlorine is having the, we know that already we discussed in our previous classes, atomic number is 17, electronic configuration neon 3s2, 3p5, where chlorine is having the one of the unpaired electron in its valence p orbital. So the p orbital electron of the chlorine overlaps with the all these 5 SP3d hybrid orbitals of the phosphorus along the internuclear axis, and finally produces 5 phosphorus chlorine sigma bonds. These sigma bonds are arised by the overlapping of SP3d hybrid orbitals of phosphorus with p orbital of the chlorine. Now its equivalent structure can be written like this. This is phosphorus above and below the plane. So like this the shape is present. So these are called as trigonal planar part, and this is pyramidal part. That's why it is called as trigonal. 2 pyramids means bipyramidal shape. Here 2 type of the bonds are present. The bonds which are present on the plane are called the equatorial bonds, and the bonds present above and below the plane are called the axial bonds. So these 2 are axial bonds and these 3 are equatorial bonds. Equatorial bond angle is 120 degrees, whereas axial bond angle is 90 degrees. Since axial bonds are closer to these 3 equatorial bonds, they get more repulsion and they stretch away from the phosphorus atom. Hence, axial bond lengths are more than the equatorial bond lengths. Now, let us see the example of the SP3d2 hybridization. SP3d2 hybridization. So here, 1 s orbital intermixes with 3 p orbitals, and along with the 2 d orbitals, and produce totally 6 are present. 2 d orbitals, 3 p orbitals, and 1 s orbital. So here we will get the 6 equivalent energy SP3d2 hybrid orbitals. So these orbitals are oriented like this. These are all 6 SP3d hybrid orbitals. Shape is, if you connect these 4 orbitals are in one plane. This orbital above and below the plane, hence it is called the octahedral. Let us take an example here. Example is SF6 molecule. Sulfur atomic number is 16. Electronic configuration neon 3s2, 3p4, 3d0. So sulfur is having the 2 s electrons, 4 p electrons, and no d electrons. But to get the 6 bonds, sulfur needs to create 6 unpaired electrons. That means here, when electron jumps from the p orbital to d orbital, it is called the first excited state. And this electron also, when jumps to the d orbital, it is called the second excited state. So if you directly write down the second excited state electronic configuration of the sulfur, here we get the 3s1, 3p3, 3d2 electrons. S orbital 1 electron, p orbital 3 electrons, and d orbital 2 electrons are present. So the intermixing of these orbitals produce SP3d2 hybrid orbitals. And in the earlier case when we were discussing, I said that 3s orbitals, 3p orbitals can mix with the 3d orbitals, as well as 3d orbitals can mix with the 4s and 4p orbitals. But remember that these p orbitals cannot mix with the 4s orbitals because energy gap is very much is present. That's why this energy is intermediate between both of these, hence only 3d orbital can intermix with the 3s, 3p as well as 4s and 4p. Now let's come back to this concept. So the shape of these 6 SP3d hybrid orbitals looks like this. Hence here we can write down that each of these orbital is occupied by 1 electron. Afterwards, overlap with the p orbital electron of the fluorine to get the 6 sulfur fluorine bonds. So its equivalent structure, if you write down here, sulfur is at center. All these places are occupied by the fluorine atoms. Now, why it is called as octahedral? So that if you connect like this here, octa meaning 8, hedral means faces, 8 faces. So here one face is present, left side. Similarly, when you connect, you will get one front face. And when you connect that side, so this side one, right side one triangle can be developed, that is third face. And from here to this fluorine, again this fluorine, back side, rear side also one face is developed. Totally 4 faces are developed from the above the plane. Now below the plane with this fluorine atom, we can develop 4 more faces. Totally octahedral means it is having the 8 faces. Now what is the bond angle? Bond angle is nothing but 90 degrees. Any 2 closest bonds are having the 90 degrees bond angle. So this is having the 90 degrees bond angle with all these bonds, but opposites bonds are having the 180 degrees angle. So this fluorine bond angle is 180 degrees. This fluorine bond angle is 180. This fluorine bond angle also 180 degrees. So dear students, I hope you understand my class. If you really like my class, please do subscribe the channel. So we shall meet in the next class. Thank you one and all.